If you ever check out the source code for Quake 3, you might have seen the function QRSQRT, and inside of it, this line. We are not sure who from id Software wrote it. Moreover, we are not even sure who actually invented this technique. But, well, we can guess. Let me show you what is happening here, what 5F3759DF is, and why this is such a mind-boggling stroke of genius. Quake III Arena was a big thing when released. If there is something missing in the game for you, it's not because we forgot, it's because we tried it and it didn't work. It was a miracle due to very aggressive multiplayer-based gameplay, but also a strong single-player game with bots having fantastic AI. It was fast, relatively simple when it comes to mechanics, and highly addictive. Even nowadays, Quake is the personification of pure skill. To understand why that code exists, you have to understand the bottleneck of 3D game dev. Let me mention three algorithms, pretty common in computer graphics: dynamic lighting and shading. Whenever a rocket exploded, the engine had to instantly calculate how the dynamic light bounced off walls, floors, and other players. To calculate surface brightness, 3D engines use the dot product. If vector L is the light vector and vector n is the surface normal, that dot product directly gives the cosine of the angle between them. Vector L dot vector n equals the cosine of theta. But here is the catch. The math only works if both vectors have a length of exactly 1. We call this normalization. If you are a regular viewer, this is pretty well known to you already. And if not, let's fix it and subscribe. The railgun and hitscan physics. Rockets are physical objects that fly through the map. The railgun is different. It is hitscan, meaning it hits its target instantly. To calculate a railgun shot, the engine uses raycasting. It grabs the exact position of your camera, takes the vector of where you are looking, normalizes that view vector to length of 1, and then multiplies it by the weapon's maximum range, let's say 8,192 units. This draws a perfect, invisible mathematical line through the map. If the line intersects another player's hitbox, it registers a hit. Wall sliding and collision. Quake is famous for its movement. When you strafe jump diagonally into wall at high speed, you don't instantly stop dead in your tracks. You slide smoothly along the surface. This requires calculating a slide vector. The game checks the surface normal, a normalized vector pointing straight out from the wall. When your movement vector collides with it, the engine uses that normalized vector to push your character away just enough to prevent clipping, while letting your momentum carry you forward. Did you notice how I mentioned the word normalization for all of these use cases? For the mentioned vector math to work correctly, these vectors needs to be normalized. That means we have to scale them down so their direction stays the same, but their total length becomes exactly 1. How do you do that? You take the vector's components and divide them by the vector's total length. And how do you get the length? The Pythagorean theorem, which requires calculating of square root. So, to normalize a vector, you end up needing to compute 1 over the square root of a number. F of x equals 1 over the square root of x. Here is the harsh reality in 1999. Floating point division was painfully slow, and computing a floating point square root even slower. If you had to do both of these operations for thousands of polygons every single frame, your game engine felt it. So what if there is a trick to calculate x to the power of negative 0.5? Without actually doing the division or the square root. To understand the shortcut, we have to look at how computers store decimal numbers. They use the IEEE 754 standard. A 32-bit floating point isn't stored as a single continuous value. It's chopped into 3 parts: a 1-bit, which is sign, 8-bit exponent, and the 23-bit mantissa, fraction. It's basically scientific notation under the hood. What if we took that floating point number, completely ignored the IEEE standard, and just told the CPU, hey, Pretend these 32 bits are just a standard integer. Mathematically, if you take the raw bits of floating point number and interpret them as an integer, you get a surprisingly close approximation of the logarithm of that number, just scaled and shifted. Mathematically speaking, scaled and shifted, so imagine multiplication and addition. It is weird. Let me show you the code. By simply telling the C++ compiler to read the memory address of 6.25 as an integer, we get this. When we take the actual mathematical logarithm base 2 of 6.25 multiplied by 2 to the power of 23 and add the IEEE bias shift of 127 times 2 to the power of 23, we get this number. They're almost identical. The error margin between bypassing all complex math to just read the raw bits versus doing the actual heavy logarithmic calculation is less than 0.1%. This would not pass for scientific computations, but for the purposes of video games and 3D graphics, the speed benefit fully justifies the small inaccuracy. Let's look at the math we are trying to solve here. We want the inverse square root of x, which we can write mathematically with an exponent of minus 0.5. So y equals x to the power of negative 0.5. If we take the base 2 logarithm of both sides, basic logarithm rules allows us to pull that exponent down to the front. Logarithm base 2 of y equals negative 0.5 times logarithm base 2 of x. Why is this amazing? Because multiplying or dividing by 2 in binary is the easiest thing a computer can do. You just shift the bits to the right. So the algorithm takes our original float, casts it to the integer using pointers to bypass the C compiler safety checks, and bit shifts it right by 1. This perfectly divides the logarithm by 2. The negative sign simply means we will subtract it. Now, let's look at exactly where that magic constant comes from. Normally, in production code, we don't like to see magic numbers. It is considered code smell. Just imagine yourself debugging this thing in a few months. Would you remember why you put this particular value there? Well, here you can see justified exceptions. If you break down the IEEE standard, the decadic value of 32-bit floating point number x is evaluated using this exact formula. X equals 1 plus m over 2 to the power of 23, all multiplied by 2 to the power of e minus 127. Here, m is the integer value of our 23 mantissa bits, e is our 8-bit exponent, and 2 to the 23 is our scaling factor, and 127 is the IEEE exponent bias. When we take the base 2 logarithm of this entire equation to do our inverse square root rate, logarithm rules allows us to split the multiplication into addition, giving us this. Logarithm base 2 of x equals logarithm base 2 of the quantity of 1 plus m over the 2 to the power of 23 plus e minus 127. Here is the dirtiest, most beautiful trick in the whole algorithm. In mathematics, logarithm base 2 of 1 plus v is roughly just equal to v plus a tiny adjustment factor to correct the curve. Let's call it adjustment factor nu. Let's substitute that into our equation. Logarithm base 2 of x is approximately equal to m over 2 to the power of 23 plus mu plus e minus 127. Now, watch what happens when we scale the entire equation up while multiplying everything by 2 to 23. 2 to the power of 23 times logarithm base 2 of x is approximately equal to m plus 2 to the power of 23 times e plus 2 to the power of 23 times the quantity mu minus 127. Look closely at that m plus 2 to the power of 23 e part. Because of how bits are laid out in memory, that's literally just the integer representation of our float, the raw bits. Let's call it I sub x. So our equation simplifies to 2 to the power of 23 times logarithm base 2 of x is approximately equal to I plus 2 to the power of 23 times the quantity mu minus 127. Remember our original goal. We want to find y equals x to the power of negative 0.5. which means logarithm base 2 of y equals negative 0.5 times logarithm base 2 of x. Let's substitute our brand new integer approximation into both sides of that equation. Iy plus 2 to the power of 23 times the quantity mu minus 127 is approximately equal to negative 0.5 times the quantity ix plus 2 to the power of 23 times the quantity mu minus 127. If we run the basic algebra to isolate iy, the raw integer bits of our final answer, we get this beautifully consolidated formula. I sub y is approximately equal to 3 halves times 2 to the power of 23 times the quantity 127 minus mu minus 1 half times ix. That's right here. That is the Holy Grail. Look at the right side. Negative 1 half times ix is exactly what the code is doing when it bit shifts the integer to the right by 1. And that giant chunk of constants on the left, 3 halves times 2 to the power of 23 times the quantity 127 minus mu. If you plug in a value of roughly 0.045 for mu to perfectly minimize the error margin of our linear approximation, that entire expression evaluates to exactly this. Convert that number to hexadecimal, and what do you get? 5f, 3759 df. The magic constant is just the perfectly pre-calculated offset to hack the IEEE 754 standard. It corrects the error of pretending a float is an integer while doing logarithmic math. The bit trick gets us a result with about 1% error rate. Worse than for the pure logarithm. I mean, 1% is still good, but for 3D graphics, it can cause visual artifacting. To polish this approximation, the code finishes with one single iteration of the Newton-Raphson method. The generic calculus formula looks like this. In plus 1 equals in minus f of yn divided by f prime of yn. You take your current guess, yn, and you subtract the function evaluated at that guess divided by its derivative. But that generic formula has division in it. The whole point of this algorithm was to avoid division, because it is slow. Here is where the math gets beautiful. We get to choose how we frame the function. We want to find y equals 1 over the square root of x. If we square both sides, we get y squared equals 1 over x. If we rearrange this to isolate 0, we get the function we need to find the root of. F of y equals 1 over y squared minus x equals 0. Written with negative exponent, that is f of y equals y to the power of negative 2 minus x. Now we need its derivative. Using basic power rules, we drop the minus 2 to the front and subtract 1 from the exponent. The constant x disappears. F prime of y equals negative 2 times y to the power of negative 3. Let's plug our custom function and its derivative back into the generic Newton-Raphson formula. Y sub n plus 1 equals yn minus the quantity yn to the power of negative 2 minus x, all divided by negative 2 times yn to the power of negative 3. We have a negative over negative, which becomes positive. And if we pull that y to the power of negative 3 out of the denominator, it flips y cubed in the numerator. Let's simplify. Yn plus 1 equals yn plus the quantity yn cubed times the quantity yn to the power of negative 2 minus x, all divided by 2. Now, let's distribute this y cubed through the parentheses. Yn plus 1 equals yn plus the quantity yn minus x times yn cubed, all divided by 2. Split the fraction so we can clearly see our terms. Yn plus 1 equals yn plus 0.5 times yn minus 0.5 times x times yn cubed. Combine the y sub n terms to get 1.5 times yn, and finally factor out a single yn from the entire equation. Yn plus 1 equals yn times the quantity 1.5 minus 0.5 times x times yn squared. Look at that final formula. The division is completely gone. There are no square roots. There are no fractions. Just a few multiplications and a single subtraction. In the actual Quake C code, they even pre-calculated 0.5 times x and stored it in a variable called x2 specifically, so the CPU wouldn't have to calculate it on the fly. Because our initial guess from the magic constant was already so close, passing it through this Newton-Raphson formula just one time drops the error margin from roughly 1% down to 0.17%. Code that runs at the speed of light, well then calculus. This hack allowed games to render complex lightning and physics on, by today's standard, ancient hardware. Today, we don't write this code anymore. Modern GPUs and CPUs have dedicated hardware instructions like reciprocal square root of scalar singular precision floating point in x86 that compute this instantly at the silicon level. But still, this algorithm remains a beautiful reminder that when you strip away the abstractions, when you truly understand how computers work at the bare metal level, how bits are physically structured in memory, you can optimize to absurd measures. And optimizing is an incredibly attractive activity for a graphics developer. Maybe you want to start with graphics development but not sure where? Check out this and spin the cube. If you like what you saw and want to see more in the future, feel free to subscribe, like, comment, or even become a member if you want to support the channel. Thanks for watching, and ciao!